And now in this lecture I'll answer on two questions. In the first question we find out the size of this angle x, and in the second question we find out the area of the green shape. So let's start with the first question. In the drawing we have a quarter circle, and inside the quarter circle we have angle APQ, that is a right angle. Angle AOB is also a right angle because AOB is a quarter circle. And we know that AP equals to PQ. And our test is to find out the size of this angle, angle PQB, that equals to x degrees in its size. So we have to find out the size of angle x. So first of all, we will complete the quarter circle to a semicircle. And we define this point as point M. So actually AM is the diameter of this semicircle according to our construction. Because we completed the quarter circle to a semicircle, therefore AM is the diameter of the semicircle according to our construction. AM is the diameter of the semicircle. So in the next step, we know that AM is a diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the areas must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the areas on one side of a straight line is equal to 180 degrees. So which areas we have at the right side of the straight line AM at point O? We have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will extend line segment PQ by straight line until it touches the semicircle. But the question is, well, the extended line segment PQ will touch the semicircle. We will assume that the extended line segment PQ will touch the circle at this point, point L. But it is actually impossible that the extended line segment PQ will touch the semicircle at this point, point L. Why? Because then we will have peripheral angle APQ that is equal to 90 degrees in its size. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subset of the diameter of the semicircle or a circle. But here, if the extended line segment PQ will touch the circle at point N, then peripheral angle APL subset on AL. Peripheral angle APL subset on AL, and the size of peripheral angle APL is 90 degrees. And we have the rule that any peripheral angle, rule 5, that any peripheral angle that is equal to 90 degrees in its size must subset on the diameter of the semicircle or a circle. But here AL, peripheral angle APL subset on AL, and AL is definitely not the diameter of the semicircle. Why? Because the center of this semicircle is here at point O. And we know that any diameter of the circle or a semicircle must pass through the center of the circle. And here AL definitely doesn't pass through point O. So AL is not the diameter of the semicircle, so we have here contradiction to rule 5. Because one, we have peripheral angle APL that is equal to 90 degrees in its side, and still it doesn't subtend on the diameter of the semicircle because it subtends on AL, and AL cannot be the diameter of the semicircle because it doesn't pass from point O, that is the center of the semicircle. So it is impossible that the extended line segment PQ will touch the circle at point L. So we cancel this option. Now we will assume that the extended line segment PQ will touch the circle at this point that we will define as point H. Here we also will have contradiction to rule 5. Why? Because we have here peripheral angle APH that is equal to 90 degrees in size, and it's subtended on AH. Peripheral angle APH subtended on AH. And AH is definitely not the diameter of the semicircle because AH doesn't pass from point O, that is the center of the semicircle. Again, AH is not the diameter of the semicircle, and it is contradiction to rule 5. One, because we have peripheral angle APH that is equal to 90 degrees in its side, and still it doesn't subtend on the diameter of the semicircle because AH is not the diameter of the semicircle because it doesn't pass from point O, that is the center of the semicircle. So due to those contradictions to rule 5, we have to derive from the contradictions to rule 5 that the extended line segment PQ will touch the semicircle at point M and only at point M. And again, due to the contradictions to rule 5, we conclude that the extended line segment PQ will touch the semicircle at point M and only at point M and not in any other point. Now it doesn't have any contradiction to rule 5. One, because we have peripheral angle APM that is equal to 90 degrees in its size, and peripheral angle APM subtends on AM, that is the diameter of the semicircle. AM is the diameter of the semicircle according to our construction. And again, we have to conclude that the extended line segment PQ will touch the semicircle at point M. Now we don't have contradiction to rule 5 because we have peripheral angle APM, that is the right angle, and it indeed subtends on AM, that is the diameter of this semicircle, exactly according to rule 5. Okay, so in the next step, we'll join points A and Q together by straight line. By joining points A and Q, we created the right triangle and the associated triangle, triangle APQ. Repeat again, by joining points A and Q together by straight line, we created the right associated triangle, triangle APQ. Triangle APQ is the right angle because angle APQ is right angle, and triangle APQ is also an associated triangle because side AP equals to side PQ. We know that the sum of the angles in a triangle is equal to 180 degrees. So in the right triangle APQ, the sum of the angles must be equal to 180 degrees. And we have the rule that in front of equal sides in the triangle there are equal angles. So if you relate to the right triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we have the rule that the sum of the angles in a triangle is equal to 180 degrees. So which angles we have in the right associated triangle, triangle APQ? We have this angle that is a right angle plus alpha, that is plus 2 alpha. In total, they must be equal to 180 degrees, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2 is 45 degrees. So this is angle alpha that equals to 45 degrees in size. And this is also angle alpha that equals to 45 degrees in its size. In the next step, we'll prove that the right triangle AOQ can point to the right triangle OQM according to side angle side rule. So as you know, we'll prove that the right triangle AOQ can point to the right triangle OQM according to side angle side rule. So why those two right triangles can point to each other? First of all, AO equals to OM. Side AO equals to side OM. They are both the radius of the semicircle, therefore they are equal to each other. We define the radius of this semicircle as R, so OM equals to R, AO also equals to R. Repeat again. Side AO of the right triangle AOQ equals to side OM of the right triangle OQM. They are both the radius of the semicircle, therefore they are equal to each other. In addition, those two angles are both right angles, therefore they are equal to each other. This is angle AOQ in the right triangle AOQ, and it is equal to this angle, that is actually angle QOM in the right triangle OQM. Repeat again, let us now know that angle AOQ in the right triangle AOQ is equal to angle QOM in the right triangle OQM. They are both equal to 90 degrees and therefore they are equal to each other. And finally, side OQ is a common side that belongs to both triangles. So you can write down that OQ equals to itself as a common side that belongs to both triangles. OQ equals to OQ as a common side that belongs to both triangles. So if we prove that triangle AOQ can go into triangle OQM according to side angle side rule. Triangle AOQ can point, this is the sign of can point, to triangle OQM according to side angle side rule. That is to say, we have to prove that those two sides and the angle that is included between those two sides in the right angle AOQ are correspondingly equal to those two sides and the angle that is included between those two sides, that is this angle, in the right angle OQM. Therefore, those two right angles can go into each other according to side angle side rule. And from the fact that those two right angles can go into each other, we will derive that side AQ or triangle AOQ is equal to side QM or triangle OQM. AQ equals to QM. Actually, AQ equals to QM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore the two corresponding sides, that is to say AQ and QM, are also equal to each other. So if we relate to the big triangle AMQ, the big triangle AMQ, side AQ equals to side QM. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in triangle AMQ, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. In the next step, we present to you a new rule and we implement the new rule in our drawing. The new rule is rule 8. According to rule 8, an exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. So in the drawing, we have triangle ABC that could be any triangle. Those three angles alpha, beta, and gamma are defined as interior angles of triangle ABC because they are located inside triangle ABC. While this is angle E that is defined as an exterior angle because angle E is outside triangle ABC. And according to this rule 8, the size of angle E, the exterior angle E, actually angle E is angle ACF that is equal to E degrees in its size. So the size of angle E is equal to the sum of the two angles that are not adjacent to it. This is angle gamma that is definitely adjacent to angle E. The two other integers that are not adjacent to it are alpha and beta. So the size of the exterior angle E is equal to the sum of the two integers that are not adjacent to it. That is to say alpha plus beta. So the size of the exterior angle E is equal to alpha plus beta. So we can implement rule 8 in our drawing. Why? Because in our drawing, if we relate to triangle AQM, this is triangle AQM, angle AQP, this angle is defined as an exterior angle of triangle AQM because it is not located inside triangle AQM, but it is located outside triangle AQM. Therefore, it is defined as an exterior angle of the triangle AQM. So the size of angle AQM, according to rule 8, so in relation to the big triangle AQM, this big triangle AQM is actually an associated triangle because AQ equals to QM. So the size of the exterior angle AQP is equal to the sum of the two angles that are not adjacent to it. This is angle AQM that is definitely adjacent to angle AQP. The two other triangles that are not adjacent to angle AQP are those two angles. beta and beta. And according to rule 8, the size of the external angle, angle AQP, is equal to the sum of the two internal angles that are not adjacent to it. That is to say, it's beta plus beta. So the size of the external angle, angle AQP, is equal to beta plus beta, that is 2 beta, according to rule 8. But we have already found out that the size of angle AQP is equal to 45 degrees. So we can substitute angle AQP by 45 degrees. So 45 degrees equals to 2 beta. Here we divide this equation by 2. And finally we get that the size of angle beta is equal to 45 degrees over 2 is 22.5 degrees. So the missing angle beta is equal to 22.5 degrees in its size. Likewise, this is angle beta that is equal to 22.5 degrees in its size. In the next step, we'll focus on the right triangle OQM. The sum of the angles in the right triangle OQM must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle OQM? We have this angle that is the right angle, that is to say it is equal to 90 degrees in its size, plus this angle that is equal to beta, and beta equals to 22.5 degrees in its size, plus this missing angle that is actually angle OQM. So the sum of those three angles must be equal to 180 degrees according to the rule that said that the sum of the angles in a triangle is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that 22.5 degrees plus the missing angle OQM in total is equals to 180 degrees minus 90 degrees, it is 90 degrees. So 25.5 degrees plus the missing angle OQM in total it is equals to 90 degrees. Here we subtract 22.5 degrees from this equation, and we get that the missing angle OQM is equal to 90 degrees minus 22.5 degrees, it is equal to 67.5 degrees in its size. Okay, this is the missing angle OQM that equals to 67.5 degrees in its size. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So angle OQM equals to 67.5 degrees in its size. And it is equal to this vertex angle, angle PQB, that is equal to x degrees in its size. That is the angle that we are looking for in this question. So those two vertex angles are equal to each other. That is to say, x equals to 67.5 degrees in its size. X equals to 67.5 degrees in its size, according to the rule that vertex angles are equal to each other. So the answer to the question is the angle that we're looking for in this question. That is this angle angle x is equals to 67.5 degrees in its size. So finished with the first question. In the next step, I present to you the second question and we'll solve the second question of this lecture. In the second question, our test is to find out the area of this green shape. So in the drawing, we have a semicircle. This is a semicircle, and inside the semicircle we have two squares. Square ABCD, the big square ABCD, and the small square MEFC. We know that PQ equals to 10 units in its length. PQ is the diameter of this semicircle. That is equals to 10 units in its length. If the diameter is 10, then the radius must be equal to 5. So the radius of this semicircle equals to 5 units in its length. So I write it down. The radius of the semicircle is equal to the diameter 10 over 2, that is 5. So the radius of this semicircle is equal to 5 units in its length. In the next step, we define the center of this semicircle. This point is point O. We define the small line segment OC as X. We define one side of this square ABCD, the big square ABCD, as A. That is to say, one side of this square ABCD equals to A units in its length according to our definition. And we define the length of one side of the small square MEFC is B. So CF equals to B and EF also equals to B because all the sides of any square are equal to each other in their lengths. What is the length of the missing line segment BO? BO equals to BC minus OC. Again, BO equals to BC minus OC. So I write it down. The missing side BO is equal to BC minus OC. So in total, BO equals to BC. BC equals to A units in its length because it is one side of square ABCD minus OC. OC equals to X units in its length according to our definition. So in total, we have found out that the length of the missing side BO is A minus X units. In the next step, we join points A and O together by a straight line. Point O is the center of this semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle that is equal to 5 units in its length, according to what we have already found out. The radius of this semicircle equals to 5 units in its length. So AO equals to 5. In the next step, we join points O and E together by a straight line. OE is of course the radius of this semicircle that is equal to 5. Repeat again, OE is the radius of this semicircle that is equal to 5 units in its length. We know that all the angles in any square are right angles. So this is angle EFZ. This is equal to 90 degrees in size because MEFC is a square. Likewise, ABCD is the big square, therefore this angle is also a right angle. So in the next step, we implement the Pythagoras theorem in the right triangle ABO and in the right triangle EOF. Repeat again, we implement the Pythagoras theorem in the right triangle ABO and in this right triangle EFO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I'll copy the right triangle ABO in a new page and implement on it the Pythagoras theorem. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right triangle ABO that are going through the original drawing. According to the Pythagoras theorem, in this right triangle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So now write it down. This will be equation 1. So AO squared, that is the square of the hypotenuse, is equal to AB squared plus BO squared. The hypotenuse AO equals to 5 units in its length, therefore AO squared is 5 squared, that is 25. And it is equals to AB squared. AB is A, therefore AB squared is A squared plus BO squared. BO equals to A minus X units in its length, therefore BO squared is equal to A minus X squared units in its length. In total, according to equation 1, we have found out that 25 equals to A squared plus A minus X squared. In the next step, I'll copy the right triangle OEF, this right triangle in the new page, and we implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. Side OF equals to, in total, X plus B. the hypotenuse OE equals to 5 units in its length. So three, this is the right triangle OEF that is going to the original domain. According to the quadratic theorem, this right triangle OEF, EO squared, that is the square of the hypotenuse, equals to EF squared plus FO squared. So EO squared, that is the square of the hypotenuse, is equal to EF squared plus OF squared. EO is 5, therefore EO squared is 5 squared, that is 25, and it is equals to EF squared. EF is B, therefore EF squared is B squared, plus OF squared. OF equals to X plus B, therefore OF squared equals to X plus B squared. So in total, according to equation 2, we actually found out that 25 equals to B squared plus X plus B squared. Well, according to equation 1, 25 equals to A squared plus 8 minus X squared. In the next step, we get equation 3 that states that 25 according to equation 1 must be equal to 25 according to equation 2. So I write it down. According to equation 3, according to equation 1 must be equal to 25 according to equation 2. According to equation 1 equals to A squared plus A minus X squared. And it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. B squared plus X plus B squared. So in total, according to equation 3, we found out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here we will open the brackets on both sides of this equation, equation 3, and we get that A squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2 times A times X. And this is equals to B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation 3, so X squared will get cancelled. In this side of equation 3 we have A squared plus A squared, that is 2A squared minus 2AX equals to, in the other side of this equation 3 we have B squared plus B squared, that is 2B squared plus 2XB. So in total, according to equation 3, we found that the 2A squared minus 2AX equals to 2B squared plus 2XB. Here we will add 2AX to this equation, and we get that 2A squared equals to 2AX plus 2BX plus 2B squared. So here we subtract 2b squared from this equation, equation 3, and we get that according to equation 3, two a squared minus 2b squared equals to 2ax plus 2bx. It again, if you found out that according to equation 3, 2a squared minus 2b squared equals to 2ax plus 2bx. Here we divide this equation 3 by 2, and we get that according to equation 3, a squared over 2 is a squared, minus 2b squared over 2 is minus b squared, and it is equals to 2ax over 2 is ax, plus 2bx over 2 is bx. So in total, according to equation 3, we found out that a squared minus b squared equals to ax plus bx. We know that a squared minus b squared equals to a plus b times a minus b. It is very famous algebraic identity. And here we take x as a common factor from those two expressions. So inside the brackets we left only with a plus b. A and b. A is the length of one side of the big square, and b is the length of one side of the small square. Therefore, they are positive numbers. A and b are positive numbers. When you add two positive numbers to each other, the result must be a positive number. That is to say, a plus b can never be equal to 0. And therefore, we can divide this equation 3 by a plus b, because it can never be equal to 0. So a plus b over a plus b is 1, so a plus b will get cancelled. In this side of equation 3, we left only with a minus b equals to x times a plus b over a plus b equals to x. So in total, we found out that according to equation 3, a minus b equals to x. We'll add to this equation 3b, and we get that a equals to x plus b. Here we will subtract from this equation 3x, and we get that according to equation 3, a minus x equals to b. According to equation 3, we found out that a minus x equals to b, and a minus b equals to x. Our test is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape is equal to the area of the semicircle minus the area of the big square ABCD minus the area of this small square MEFC. So repeat again, we found out that the area of this ring shape is equal to the area of the semicircle minus the area of the big square ABCD minus the area of the small square MECF. We know that the area of any semicircle equals to pi r squared, that is the area of the circle over 2. So the area of this semicircle must be equal to pi r squared over 2. But we have only found out that the radius of this semicircle equals to 5. So r is 5, therefore r squared is 5 squared, that is 25. So in total, the area of this semicircle equals to 25 pi over 2 square units. Minus the area of the big square ABCD. We know that the area of any square equals to the length of one side squared. The area of any square equals to the length of one side squared. The length of one side, according to our definition, is A. Therefore, the length of one side squared equals to A squared. So it is minus A squared, that is the area of the big square, minus the area of the small square MEFC. The length of one side of this square MEFC is B, therefore the area of square MEFC equals to B squared. So in total, we shall find out that the area of the green shape equals to 25 pi over 2, that is the area of the big semicircle, minus A squared, that is the area of the big square, minus B squared, that is the area of the small square, MEFC. So here, the area of the green shape equals to 25 pi over 2. So here we take out minus 1 as a common factor of those two expressions. So inside the brackets we have A squared plus B squared. So in total, we found out that the area that we are looking for this question, that is the area of the green shape, equals to 25 pi over 2 minus A squared plus B squared. So we have already found out actually that A minus X equals to B. And according to equation 1, we should found out that 25 equals to A squared plus A minus X squared. And again, according to equation 1, we already found out that 25 equals to A squared plus A minus X squared. So according to equation 1, we should find out that 25 equals to A squared plus A minus X squared. We already found out that A minus X equals to B. If A minus X equals to B, it means that A minus X squared must be equal to B squared. Okay, A minus X squared must be equal to B squared. So we can substitute a minus x squared in this equation 1 by b squared. So in total we should find out that a squared plus b squared equals to 25. According to equation 1, a squared plus b squared equals to 25. And therefore in total they have the green shape equals to 25 pi over 2 minus a squared plus b squared. But we already found out that a squared plus b squared equals to 25. So we substitute a squared plus b squared by 25. So in total we should find out that the area that we are looking for this question is equals to 25 pi over 2 minus 25. In terms of numbers, the value of this expression is 14.27 square units in its size. Okay, again, we should find out that the area of this green shape is equal to either 25 pi over 2 minus 25 square units, so in terms of numbers, the area of this green shape is equal to 14.27 square units in its size. So we finish with the second question. In the next step, we start out the lecture. We start with the first question, of course. In the first question, our task is to find out the size of this angle x. Angle PQB is equal to x degrees in its size. So in the drawing, we have a quarter circle. AOB is a quarter circle. Inside this quarter circle, this is angle APQ that is equal to 90 degrees in its size. This angle AOB also equals to 90 degrees in its size because AOB is a quarter circle. In addition, we know that AP equals to PQ. Again, our task is to find out the size of this angle PQB that is equal to x degrees in its size. So in the first step, we completed the quarter circle to a semicircle. So this is the semicircle. This is a semicircle, therefore AM is the diameter of this semicircle according to our definition. AM is the diameter of the semicircle according to our definition. So AM is the diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have on the right side of AM at point O? We have this angle that is the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the next step, we join points A and Q together by straight line. By joining points A and Q, get the right angle that is also an associated triangle. Triangle APQ is a right angle because angle PQ equals to 90 degrees, and triangle APQ is also an associated triangle because side AP equals to side PQ. And we know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right and associated triangle APQ? First of all, we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be equal to alpha because they are equal to each other. So the sum of the angles in the right triangle APQ equals to 180 degrees. So which angles we have on the right side? Which angles we have in the triangle APQ? We have this angle that is right angle plus alpha that is 2 alpha. Total they must be equal to 180 degrees. So in total we should find out that 90 degrees plus 2 alpha equals to 180 degrees. If subtract 2 alpha from this equation, if I found out that 2 alpha equals to 180 degrees, 190 degrees is 90 degrees. 2 alpha equals to 90 degrees. If we divided this equation by 2, if I found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is the missing angle alpha, that is equals to 45 degrees in size. And this is also the missing angle alpha, that is equals to 45 degrees in its size. So, in the next step, we prove that the right triangle AEOQ can go into the right triangle OQM according to side angle side rule. So, we actually prove that those two right triangles can go into each other. Why those two right triangles can go into each other? First of all, side AEO of the right triangle AEOQ equals to side OM of the right triangle OQM. They are both the semicircle because therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, side OQ is a common side that belongs to both triangles. So we can write down that OQ equals to itself is a common side that belongs to both triangles. So if you prove that those two right triangles can go into each other according to side angle side rule, where those two sides, that the angle between those two sides in the right triangle AEOQ corresponding equal to those two sides, and the angle that is included between those two sides in the right triangle OQM. Therefore, those two right triangles can go into each other according to side angle side rule. And again, if we found out that the right triangle AEOQ can go in, this is the side can go into the right triangle OQM according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that side AQ of the right triangle AEOQ equals to side QM of the right triangle OQM. AQ equals to QM. AQ equals to QM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other. According to the rule that corresponding sides in congruent triangles are equal to each other. So AQ equals to QM. So if you relate to the big triangle AQM, in the big triangle AQM, side AQ equals to side QM. And we have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and it is true also in triangle, the big triangle AQM. So which angles we have in the big triangle AQM? We have beta plus beta, that is 2 beta. And actually we implemented rule 8 in our drawing. So first of all, in front of those two equal size, we have those two angles that are equal to each other in their sizes. So if the size of this angle is better, then the size of this angle must be also equal to beta because they are equal to each other. So if we relate to the big triangle AQM, those three angles are interior angles, and this is an exterior angle of triangle AQM because it is located outside triangle AQM. So according to rule 8, an exterior angle of a triangle is equal to the sum of the two triangles that are not adjacent to it. So this is triangle ABC that could be any triangle. These triangles alpha, beta, and gamma are defined as interior angles because they are located inside triangle ABC, while this is angle E. Angle ACB equals to 8 degrees in its size according to our definition. Angle E is defined as an exterior angle of triangle ABC because it is located outside triangle ABC. So according to this rule 8, the size of this angle, the exterior angle E, is equal to the sum of the two interior angles that are not adjacent to it. Angle gamma, this is angle gamma that is definitely adjacent to angle E. The two other interior angles that are not adjacent to it are alpha and beta. So according to this rule 8, the size of this angle E, the exterior angle E, is equal to the sum of the two interior angles that are not adjacent to it. Which is to say alpha plus beta equals to angle E according to this rule 8. So can we implement rule 8? Can implement rule 8 in our drawing? Why? Because in our drawing we have the exterior angle AQP. According to rule 8, the exterior angle AQP must be equal to the sum of the two interior angles that are not adjacent to it. This is angle AQM that is definitely adjacent to this angle AQP, and the two other interior angles that are not adjacent to it are those two angles. This is angle beta, this is also angle beta. So beta plus beta equals to the exterior angle AQP according to rule 8. And again, according to rule 8, in the big triangle AQM, according to rule 8, the exterior angle AQP, this is the exterior angle AQP that is equals to beta plus beta. The exterior angle AQP equals to beta plus beta, that is 2 beta according to rule 8. But we have already found out that the exterior angle AQP equals to 45 degrees in size. So we can substitute AQP by 45 degrees. So in total, we found out that 45 degrees equals to 2 beta. Here we divided this equation by 2 and finally found out that the size of angle beta is 22.5 degrees. This is angle beta that equals to 22.5 degrees in size. This is also angle beta that equals to 22.5 degrees in its size. We know that the sum of the angles in an triangle is equal to 180 degrees. It is true in an triangle, and especially it is true in the right triangle QOM. So which angles we have in the right triangle QOM? We have this angle that is right angle, plus this angle that equals to 22.5 degrees in size, plus this missing angle that is angle OQM. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle OQM, 90 degrees plus 22.5 degrees, plus the missing angle OQM, in total it must be equal to 180 degrees. Here we subtract the 90 degrees from this equation and found out that 180 degrees minus 90 degrees is 90 degrees. So 22.5 degrees plus the size of the missing angle OQM, in total must be equal to 90 degrees. Here we subtracted 22.5 degrees from this equation and finally found out that the missing angle OQM, this is the missing angle OQM, is equal to 90 degrees minus 22.5 degrees is 67.5 degrees. So this is the missing angle OQM that equals to 67.5 degrees in its size. Now we have Those two angles are defined as vertex angles, and you know that the vertex angles are equal to each other. The size of this vertex angle is 67.5 degrees, and the size of this vertex angle is x. X is the angle that we're looking for in this question. So those two angles are equal to each other in their sizes. That is to say, x equals to 67.5 degrees in its size. Okay, if you found out that according to the rule that vertex angles are equal to each other, those two angles are equal to each other. That is to say, x equals to 67.5 degrees in its size. And that is the answer to the first question. The size of this angle x is 67.5 degrees. So we finish with the first question. In the next step I present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this gun shape. So in the drawing, we have a semicircle. This is a semicircle. Inside the semicircle, we have the big square ABCD and the small square MEFC. Again, our task is to find out the area of this gun shape that is inside this semicircle. So first of all, we define one side of the big square as A. That is to say, AB equals to BC equals to CD equals to AD equals to A units in its length. Likewise, we define one side of the small square MEFC as B. That is to say, EF equals to CF equals to CM equals to ME, and each side equals to B units in its length according to our definition. We defined the center of this semicircle. This point is point O. It's given us the question that PQ equals to 10. PQ is the diameter of this semicircle, that is 10. If the diameter is 10, then the radius must be equal to 10 over 2, that is 5. So the radius of this semicircle equals to 5 units in its length. So in the next step, so AB equals to A units in its length, also equals to X according to our definition. So BC must be equal to BC equals to BO actually this is the missing side BO. BO equals to BC minus OC. Again, BO equals to BC minus OC. And again, BO equals to BC minus OC. So BO, this is the missing side BO, it is equals to BC. BC is A according to our definition, minus OC. OC is X also according to our definition. So in total, the missing side BO equals to A minus X units in its length. What is the size of this line segment OF equals to X plus B. In the next step, we join points O and A together by straight line, and join points O and E together by straight line. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of the semicircle that is equals to 5 units in its length, because the diameter is 10, therefore the radius is 5. Likewise, OE is also the radius of the semicircle that is equals to 5 units in its length. So in the next step, I copy the right triangle ABO. In the new page, I implemented the Pythagoras theorem and right triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So okay, this is the right triangle ABO that I copied from the earlier drawing. According to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25. And it is equals to AB squared. AB is A, therefore AB squared is A squared, plus BO squared. BO is A minus X, therefore BO squared equals to A minus X squared. So in total, according to equation 1, we found out that 25 equals to A squared plus A minus X squared. Likewise, I copied the right triangle EFO in a new page and implemented the Pythagoras theorem on this right triangle EFO. So actually this is right line EFO with the copy from the original domain according to the Pythagoras theorem. In this right line EFO, E all squared, that is the square of the hypotenuse, equals to EF squared plus F all squared. E all squared equals to EF squared plus F all squared. EO is 5, therefore EO squared is 5 squared, that is 25, and this is equals to EF squared. EF is B, therefore EF squared is B squared, plus OF squared. OF is X plus B, therefore OF squared is X plus B squared. So according to equation 2, I shall find out that 25 equals to B squared plus X minus B squared. This is according to equation 2, while according to equation 1, we have only found out that 25 equals to A squared plus A minus X squared. The next step, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. Repeat again, we created equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A squared plus A minus X squared. A squared plus A minus X squared. And it must be equal to 25 according to equation 2. We only found out that 25 according to equation 2 equals to B squared plus X plus B squared. Here we open the brackets on both sides of this equation, equation 3, and found out that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared plus 2 times A times X. And on the other side of the equation 3, we have B squared plus X plus B squared. B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. Here we have X squared on both sides of this equation 3, so X squared will get cancelled. And finally found out that A squared plus A squared is 2A squared minus 2AX equals to B squared plus B squared is 2B squared plus 2XB. So in total according to equation 3, we found out that 2A squared minus 2AX equals to 2B squared minus 2XB. Here we added 2AX to this equation, equation 3, and found out that 2A squared equals to 2AX plus 2B squared plus 2XB. Here we subtracted 2B squared from this equation, equation 3, and found out that 2A squared minus 2B squared equals to 2AX plus 2XB. Here we divided this equation, equation 3 by 2, and found out that 2A squared over 2 is A squared minus 2B squared over 2 is minus B squared equals to 2AX over 2 is AX plus 2XB over 2 is XB. So in total according to equation 3, we found out that A squared minus B squared equals to AX plus B squared. Again, A squared minus B squared equals to AX plus BX. Here we have the famous algebraic identity that says that A squared minus B squared equals to A plus B times A minus B. And it is equals to, here we took X as a second factor from those two expressions, so inside the brackets we left only with A plus B. So according to equation 3, in total we found out that A plus B times A minus B equals to X times A plus B. Here we divided this equation, equation 3 by A plus B. Why it is allowed to divide by A plus B? Because we know that A is the length of the one side of the big square BCD, and B is the length of the small square MFEC. When you add two positive numbers to each other, the result must be a positive number. So A plus B can never be equal to 0. It must be a positive number, therefore it is allowed to divide this equation by A plus B. So we divided this equation by A plus B. A plus B times A minus B over A plus B is A minus B, and it is equals to X times A plus B over A plus B is X. So in total, according to equation 3, we found out that A minus B equals to X. Here we divided this, we added to this equation, equation 3b, and finally found out that A equals to X plus B. So here we subtracted X from this equation, equation 3, and finally found out that A minus X equals to B. So according to equation 3, A minus X equals to B, A minus B equals to X. Here we have, according to equation 1, we have already found out that, according to equation 1, we have already found out that 25 equals to A squared plus A minus X squared. And again, according to equation 1, 25 equals to a square. 25 equals to a square plus a minus x square. So here we have, according to equation 1, 25 equals to a square plus a minus x square. So a minus x equals to a minus x equals to b. If a minus x equals to b, it means that a minus x square must be equal to b square. A minus x square must be equal to b square. Again, our test is to find out the area of this green shape. The area of the green shape equals to the area of the big semicircle minus the area of the big square minus the area of the small square. And again, the area of this green shape must be equal to the area of the big semicircle minus the area of the big square ABCD minus the area of the small square MEFC. So the area of the green shape equals to the area of the semicircle. The area of any semicircle equals to the area of the circle that is pi r squared over 2. We already found out that the radius of the semicircle is 5, therefore pi r squared over 2 is 25 pi over 2. Now the area of this big square ABCD. One side of square ABCD equals to a units in its length. Therefore the area of this semicircle is a square. Now the area of this square ABCD equals to a square minus the area of this small square MEFC. The area of one side of this square MEFC is b, therefore the area of the small square MEFC equals to b square. So in total we can find out that the area of the semicircle and the area of the green shape equals to the area of the big semicircle that is 25 pi over 2 minus the area of the big square that is a square minus the area of the small square that is b square. So it is 25 minus, here we took minus 1 as a common factor for those two expressions, so inside the brackets we left only a square plus b square. But we already found out that according to equation 1, 25 equals to a square plus x, 25 equals to a square plus a minus x square. We already found out that a minus x equals to b. If a minus x equals to b, it means that a minus x square must be equal to b square. A minus x square equals to b square. So here we can substitute a minus x square by b square. In total we can find out that 25 equals to a square plus b square. Okay, 25 equals to a square plus b square. Therefore we can substitute a square plus b square by 25. We did it and we found out that the area of the green shape in total equals to 25 pi over 2 minus a square plus b square, that is 25. So in total we found out the area of the green shape, that is the area that we are looking for in this question. It is equal to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the area of this green shape equals to 14.27 square units in its size. Okay, again, the area of this green shape equals to either 25 pi over 2 minus 25 square units. In terms of numbers, the area of this green shape equals to 14.27 square units in its size. Okay, thank you very much.